All right, welcome to our differential equations presentation 4. Module 4, we'll be looking at type of differential equation known as exact differential equations and a process using integrating factors to make them exact if they are not already. So first we need to talk about the differential form. It's another way you may see differential equations written, where rather than a typical derivative dy over dx, we see the differentials dy and dx separated like this. So we'll refer to the function of x and y in front of dx as m, and the function of x and y in front of dy as n. And here's an example of a first order nonlinear differential equation written in differential form. And you can see that m is 3x squared y squared, and n is 2x cubed y. So we can go between the differential form and maybe a more of a standard form. If we have our derivative in the prime notation, we first just switch to the Leibniz notation, and then we can split up the differentials. The term that has the derivative will get the dy, and then the other term will get the dx. And you can think of this as if you're multiplying the equation by the differential dx. All right, so here is a first order nonlinear differential equation that we may want to put in the differential form. See if you can get to the differential form and if it matches up with A, B, or C here. Pause the video if you need some more time, but we'd first want to place that prime derivative with the Leibniz notation. And then we could think of multiplying by dx. And then we can put everything on one side by maybe subtracting the left side. And that does not match any of the options there, right? Notice the first option has a plus there and we have a minus. But I think it is equivalent to answer choice C. So in answer choice C, the dy term is on the left and the dx is on the right. Usually we want the dx on the left so that we can kind of go left to right in alphabetical order with x and y and m and n. But those are in fact equivalent, and technically those are both in differential form. So I believe the correct answer here is C, though I think the way I have it written there is preferable. I've probably seen partial derivatives before, and they have their kind of curly D partial differentiation operator in the Leibniz form. But a standard prime notation is too ambiguous because with partial derivatives, you do need to specify the variable of differentiation. So the equivalent of the prime notation is the subscript notation, where you just take whatever derivative you're differentiating with respect to and make that the subscript on the dependent variable. So partial derivative of f with respect to x is f with a subscript of x. So hopefully you've seen that subscript notation before. We make use of that as we kind of set up our process here. So the idea behind the exact differential equation is that these functions m and n that appear in front of the differentials are partial derivatives of some potential function, big F of xy. Specifically, m is the partial derivative of f with respect to x, and n is the partial derivative of f with respect to y. So how would we know if that is the case, if there is such a function f where we have this relationship? Well, we take advantage of Clairaut's theorem in that if these functions are well behaved, then the second order mixed partials should be equal. So since m was the partial derivative of f with respect to x, then the partial derivative of m with respect to y is the mixed partial f xy. Similarly, in x is fyx. And Clairaut's theorem says that these should be equal under certain circumstances. So we have, again, we've given the differential equation, we can put it in differential form, we identify m and n, we can take these partial derivatives, and we can check for them being equal. And then if it's exact, we can proceed to find this function f via integration. So why don't you test if this one is exact? So it's already in the correct differential form. 3x squared y is m, and 4x cubed y is n. And again, you'd want to check that my equals nx. Right, if you need some more time, go ahead and pause the video. So the partial derivative of m with respect to y would be the partial derivative of 3x squared y with respect to y, which is 3x squared. Partial derivative of n with respect to x would be 12x squared y. So my is not equal to nx, and so the answer is no, it is not exact. So if a differential equation is not exact, all hope is not lost. We can find the so-called integrating factor. And the integrating factor is in the Trench book represented by the Greek letter mu, and is equal to base e exponential e to the integral of p of x dx, where p of x is given by my minus nx over n, if that only depends on x. So we test if it's exact first, and so we already have these same partial derivatives. And if it is exact, then that difference is 0. And then p of x is 0, and then the integral is 0, and e to the 0 is 1, and so mu is 1. But if it's non-zero, then those aren't equal, and we simplify and check to see that this is only a function of x. If it's not, the next step would be to check a similar difference quotient where we subtract the same partial derivatives the other way, but divide by m rather than n. And this is q. If q only depends on y, then we do the same thing to get mu. Integrate and then put it with a base e exponential. So you do want to learn these formulas for p and q. They are similar, and then p should only simplify to be a function of x, and q only to a function of y. If neither of those does work, there are integrating factors that involve both variables, but this is as far as we'll be going in this intro course. All right, so here is a differential equation. Again, it's first order nonlinear, and it is in differential form. And so you can easily identify m and n. And I reposted the formulas for p and q here. Go ahead and see if you can find the integrating factor for this problem. All right, pause if you need some more time. There is m, and the partial derivative of m with respect to y is negative cosine x. sine y. And then there is n, and the partial derivative of n with respect to x is cosine x cosine y minus cosine x sine y. Again, when we set up P and Q, the top is just a matter of which way we subtract. And so really what often will determine whether P or Q is in use is what we're dividing by. And since we're trying to have this go to just a function of one variable, we often want to divide by the simpler of the two functions, which in this case is m. So trying out subtracting nx minus my, we can see that the negative cosine x sine y will subtract with the negative cosine x sine y, and we'll just get cosine x cosine y. When we divide by m, we get 1, though 1 is not the correct answer, right? 1 is just q. And we see that really being a function of x or y, it means that that's the only variable that can explicitly be there. You don't have to actually see that one. You can have a constant work for either one of these. What we couldn't have there was x appearing, right? In the same way we couldn't have y appearing when we try to find p. And you might have to do some trig or algebra simplifications to make this only appear as a function of one variable. So you hopefully remember that this is just the start of the integrating factor. The actual integrating factor is e to the integral of p or q. And since it's q, it's an integral with respect to y. And so the integral of 1 dy is y. So what we do is we would actually multiply the differential equation by this integrating factor, and that would make it exact. And then you can check that putting mu there does indeed give you those relationship between those two functions so that the mixed partials are equal. So once we find mu, we would multiply there, and then it should be exact, and we proceed with solving it as an exact differential equation. So in the first methodology, we'll see how to solve an exact differential equation by integrating m and n to get f. And then when it's not exact, we can find this integrating factor mu, multiply by it, and then it makes it exact, and then we proceed solving it the same way. So those are the two methodologies for module 4. And you can proceed on to those next. Again, just attribute William Trench with the Elementary Differential Equations and Boundary Value Problems textbook, CC by NCSA. This presentation does include images and text from that book.